Okay.
3-point charges Q1, Q2, and Q3 lie among the x-axis at x equals 0, x equals 3.0 centimeters, and x equals 5.0 centimeters, respectively. Calculate the magnitude and direction of the electric force on each of the 3-point charges when Q1 equals positive 6.0
Micro
coulombs.
coulombs.
Q2 equals positive 1.5 microcoulombs, and Q3 equals negative 2.0 microcoulombs.
So the idea here is very similar to what we did in class, right? We have 3-point charges, and they are separated by given distances. This first distance here is 3 centimeters, and since this is located at 5 centimeters, it makes this 2 centimeters. If we consider this right here like the origin. Okay, that's how we're considering this. So when you hear that the first one is at x equals 0, put it on the origin. The second one is at x equals 3, you're putting it on the location x equals 3. And then x equals 5 is 2 units further to the right. So it's very similar to what we did in class. Now, we are trying to find, what does it say? The electric force on each of them. On each of them. So if you think about this, remember we did one of these examples in class? Right? We did just one of those in class, that's all. Now you're finding the electric force on all 3 particles. So you have to do kind of what we did in class 3 times. And what you're going to recognize at the end is that there's still going to be a balance of forces. So we'll see and we'll look at the sum of those forces afterwards. So let's start by looking at the first one. All right, so let's look at Q1 together. Q1. What's physically happening? This is where you have to use, so you know how I keep saying it's mathematical, but the part of it is really conceptual too. What's happening to Q1? What's happening? Somebody else, yeah.
Starting with rest.
Okay, it's currently at rest, that's true, but we're not even looking for motion right now. What is it feeling, I should say, I guess? What is it feeling?
Does it feel an attraction from Q2?
It's feeling not attraction from Q2, no, they're the same, they're both positive.
Oh,
Repulsion. What is it feeling from Q3?
attraction.
Yeah, because it's opposite signs. So if I were to analyze Q1, let's go ahead and draw Q1 by itself right here. It's feeling Q2 pushing it away. You need to remember that the same signs mean repulsion. When you have repulsion here, it means it's pushing in the opposite direction that it's from. So since Q2 is over here, and Q1 is over here, right? Q1 is getting pushed away by Q2. So draw an arrow to the left. Okay? Draw an arrow to the left. Q2 is pushing it. So it's a force on particle 1 from particle 2. The subscripts, please write the words out. If you don't understand what to do here, if this is like, you're like, what? You should physically be writing, this is a force on particle 1 from particle 2. Okay? On particle 1 from particle 2. I drew it to the left because particle 2 wants to push it away from it. It's repelling it. Particle 2 is pushing particle 1 this way. But particle 3 is all negative. And particle 3 is saying, oh, particle 1, come over here. I'm going to pull you this way. Particle 3 is the opposite sign. So it pulls particle 1 to the right. So for that one, we draw an arrow to the right. And this is from particle 3. And it's acting on, again, particle 1. Oops. Let me go back. On particle 1 from particle 3. Okay? Now, if you switch these two, it does not make a difference, as long as you're consistent within the problem. Is that clear? So if you want to write 2-1 and 3-1, say, it's from particle 3 on particle 1 instead of on particle 1 from particle 2, you can write these reversed. But all the other ones also have to be the other way around. So it does not matter if you do it the other way in your homework. I may have written them the other way in class. I don't even remember, to be honest. It doesn't matter, though, as long as you are consistent. Right? Just like if you call G negative 9.81 with projectile motion, you could have technically always called it positive. But then down would have been considered positive, which is a bit, anti or, what's the word? Anti-intuitive or counterintuitive? Counterintuitive. You wouldn't call down negative, positive. Wouldn't really make much sense. That's particle 1. Now, I'm not going to calculate these forces yet. I'm going to draw the free body diagram for all three first. Because what you're going to recognize is that if I can find F12, and then later on I need F21, it's going to be the same magnitude, right? F12 comes from Q1 and Q2. Well, it's the same answer as F21, really. They're just going to be probably opposite directions, depending on the scenario. So let's look at particle 2 now. There's particle 1, and I should put particle 1 here, right? Let's label it. Now the free body diagram on particle 2. What's happening to particle 2? Who can tell me? Conceptually, what's happening to particle 2 from the other particles around it? Paul, give me one piece.
It's getting repelled from particle 1.
Yeah. So particle 1 is positive, particle 2 is positive. So particle 2 is feeling a repulsion from particle 1. So as a result, again, we're going to say this. We're going to say that particle 2 is feeling a repulsion from particle 1. And look at F12 and look at F21. What do you notice? They're in opposite directions. It's not a coincidence. Okay? The force on particle 1, which is right here, from particle 2 is left, while the force on particle 2 from particle 1 is to the right. These are equal and opposite. Again, Newton's laws, we go back to always. These two are equal and opposite. So in a minute, when we do these calculations and we plug into the formulas, we're going to use the same number for F12 and F21, except one is going to be positive and one is going to be negative. What else is charge 2 feeling? What is charge 2 feeling? What else? Marianne? From? Yeah, take a look here. Let's go over this for a second. We want to consider particle 3 as a negative, right? So if particle 3 is negative and particle 2 is positive, they want to pull each other together. So particle 2, did you say left or right when you said it? I think it's right here. Because think about this for a second. Particle 3 is negative. It's opposite sign of particle 2. So it's going to say, all right, I want to take particle 2 and pull it toward me because I'm the opposite sign. So this one is going to feel another pull to the right in this case. So we can draw another arrow. It might be easy to draw it above it or just with another color ink maybe. But you're also going to feel something to the right from particle 3. So I'll use blue right above it so you can see the difference. And this is acting on particle 2 from particle 3. Again, look at the signs. Look at the signs. If this sign is negative and this sign is positive, they want to move toward each other. So this one feels a pull this way. This one feels a pull this way. Well, we're looking at this one right now, particle 2. It's feeling a pull to the right. That's F23. It's feeling a pull on particle 2 from particle 3. Now, again, particle 1 was repulsion, but it was on the opposite side. So it's the same direction in the end. Right? Repulsion on one side is the same as attraction on the other. Right? If a particle is over here, repelling it, it pushes it this way, doesn't it? Isn't that what repulsion means? If a particle is over here, attracting it, it pulls it this way. So in the end, both forces are acting this way, to the right, for particle 2. Okay? Let's look at particle 3 now. Let's take a look at particle 3. So let's slide this up a tiny bit more, give us a little bit of room. For particle 3, what's happening now? Particle 3 is negative, right? Particle 3 is currently negative. What are both of the other charges? Everybody. So there's attraction over here. There's no repulsion. So if I'm particle 3, and I'm standing over here, and somebody's over there that's attracting me toward them, or I'm getting pulled over by a rope, it means I'm getting pulled to the... So both of these forces are going to be drawn to the left. And it kind of makes sense because weren't both of these to the right? So you're going to have a balance of forces still. So particle 3 feels a pull to the left. It feels a pull to the left. Again, on particle 3 from particle 1, it also feels a pull to the left on particle 3 from particle 2. Okay, so in this case, we have an interesting setup to look at. We want to analyze the overall net force felt by each particle. They're going to be different, but in the end, we might notice some sort of a conclusion we can draw. Now, Let me make sure this is clear one more time. If I calculate F12, how would I find F12? Somebody give me the equation to find F12. The electric force between particles 1 and 2.
9 times...
Give me all variables for now.
So you do K, Q1, Q2 over R squared.
Good. Now, I'm going to write R12 squared, the distance between particles 1 and 2. Does that make sense? I'm going to use particle 1's charge, Q1. I'm going to use particle 2's charge, Q2. I'm going to divide it by the distance between particle 1 and 2, that's the subscript there, squared. If I want an F21, what would that equation look like? Not F12, but F21. What would F21 look like?
It would be the same except R is negative.
Okay, but you're squaring it, so it doesn't matter.
No.
So in the end, what we notice is what Paul is saying is, you're going to get the same answer for F21 as you get for F12. So I'm not going to go ahead and calculate F21. Once I get F12, I can plug that number in here, and I can plug that number in here. Please remember that we don't use the negative sign on the charge here, because we already took into account the negative and positive parts based on my free body diagram. So yesterday, remember, I put absolute value around these. If you want to do that again, do that, please. Okay, maybe it'll help you to remember that you're not really using the negative sign if there's a negative sign around them. We already took into account the negative portion of the charge by thinking of it as either attraction or repulsion. All right. That's F12. We could calculate the number we get for F12. We have to do a few other things still. We have to do F13 and then F23. And then after that, these three are all the same as the other three. So it looks like we're going to calculate 3 different forces. Okay, 3 different forces. So let's write out what F13 would look like. F13 would still be Kc, but instead of Q1 and Q2, we now have Q1 and Q3. All over the distance between particles 1 and 3 squared. Okay, again, taking a look at this, the method that we're using with free body diagrams makes this a lot easier because we don't have to consider the negative signs and think about what that means anymore. We've already taken them into account. And finally, the last part we have to do is F23. That's Kc, Q2, Q3 over R23 squared. All right, that's an R23 down there. It's hard to see that in the bottom. The equations all look the same, right? Because we're still using Coulomb's law. It hasn't changed. But our subscripts are what are important here. So we have to analyze. We know what Q1 is. We know what Q2 is. We know what Q3 is. Those numbers are just plugged in. What about that micro? What does that mean? Micro Coulomb. What do we have to do? Kira? Times 10 to the negative 6. So for example, Q1 is 6 times 10 to the negative 6. Now, what is R13? What's R13 in this problem? What's R13? Somebody hasn't answered yet. What's R13? This is not a hard question to ask. R stands for the distance between them. Look at particle 1. Steph? 5 centimeters. Particle 1 is here. Particle 3 is here. How far are they separated by? 5 centimeters. So what would you write? 0.05 meters. Okay, that's what R, and you're going to square that. Absolutely. That's what R13 is. What's R23? What's R23? The distance between particles 2 and 3. What is it? 0.02 meters or 2 centimeters. Very good. 0.02 meters or 2 centimeters. And Frank, what's R12? R12. The distance between particles 1 and 2. Look at the diagram at the top of the board. How far are particles 1 and 2 separated by?
3.
3 what? Good. So in meters, we write 0.03 meters. Okay, that's for R12. So the idea in this problem is that it's not actually difficult to do. It's the setup and plugging in the right values that is very prone to error, right? It's very easy to make a mistake on this. Now, at the end, we're going to come up with numbers. Say this is like 7 newtons, 12 newtons, 15 newtons. We then have to plug those in all these spots to find the net force on each particle. So let's go ahead and calculate what we get for each of these 3. Let's figure out what those values are. I don't need this top anymore. I'm done up here. Okay, if I can I slide this off the top? I mean, we have this all drawn. I'm going to continue and write a little bit further down. So here, again, the numerator, you know what that's going to be already. Right, what was KC? Anybody remember what KC?
9 times 10 to the 9.
9 times 10 to the 9. Very good. Is it warm or is it just me? All right, can somebody crack a window a little bit? Like dying up here. KC, it might be rounded, but on your formula sheet I have 9 times 10 to the 9. In the book, it might say like 8.97 or something like that. Whatever they use. 8.99 times 10 to the 9. Again, for the sake of a physics class, it doesn't make a difference. If you were a scientist and you were studying electricity and looking at like magnetics and circuits, sure, it would make sense. But you would use even more than 8.99. Yeah, use 9 times 10 to the 9. All right, so I'm going to write these down at the bottom here. F12. Come on, people, you should be writing this. 6 times 10 to the negative 6. 1.5 times 10 to the negative 6. All over. 0.03 squared. Did I write the right numbers down there? I couldn't see up the top. Okay, what do you get for F12? What do you get for F12? I see 1, 2, 3, 4. 4 calculators out. Let's go. Calculators out, people. Not iPads for the 100th time. So many of you fall into that trap where you can just use that writing one, which is great, but then on the test, you have to use your graphing one. What do you get for this, Mars? What do you got? 9 times 10 to the 7. Agree? Disagree? Others? Check for me. I don't have the numbers in front of me. Paul? Okay. 7.3 times 10 to the negative 5. Check again, Paul. I heard 90 from like 4 people, that's why. What do you got?
I got 90 before and then I thought that was wrong. But I did it the same way.
Let me look at the exponents. Ready? Here's how I can tell. 9 and negative 12 is going to give me negative 3. When you're squaring this, you're going to be at like negative 4. Those are going to cancel, giving you a positive 1 as an exponent. So a number like 90 is reasonable as an answer, just by looking at it. Yes, 90? Okay. If you made a mistake, go back and try and figure out what that mistake is. Again, I have not seen anybody. Tomorrow morning, our office hours, so that might be a good time. If you're struggling on this, or even if it's like typing in scientific notation, come in the morning. That's something that's easy to go over with me one-on-one. Okay? That's F12. If that's F12, that's also F21. So here, right here, and right here, you can draw 90 newtons in. Let's go ahead and do that, please. Watch. Cross this out. Put 90 newtons. Cross this out. Put 90 newtons, please. So right now, particle 1 is feeling some sort of a push or pull, in this case it was a push, to the left of 90 newtons. Particle 2 is feeling a push to the right of 90 newtons. Why is that? Because of whose law? That's Newton this time. Good. Newton's law. For every action, there is an equal and opposite reaction. Remember, F21 and F12 are equal and opposite reactions. Go ahead and calculate F13. Now, take a look. This is still going to be the same. This is the same. These are no different. Everybody, if you're doing this in your calculator in one line of entry, press second enter. It'll bring up this whole thing again. All you have to do is change this and change this. These are the same. For F13, this is still 9 times 10 to the 9, this is still 6 times 10 to the negative 6. Just change the 1.5 and the 0.03. Okay, and that'll give you F13. So I will physically draw over that so you can see what I'm saying here. So the distance between particles 1 and 3 now is 5, so this is really just 0.05 squared in the bottom now. Particle 3's charge was 2, so this becomes a 2. So take a look. I literally just did that. That's it. It's the exact same setup besides what I just changed. That's a 2 there, and that's a 0.05. Joshua, what do you got? 43. Okay, again, nothing else is changing except for what you see in red. Except for what you see in red. So get used to typing it in one line in your calculator. And then all you have to do is press second enter. It'll bring up the last entry and you can just write over it. Okay, you can type right over that entry. That's how you go through tests a lot faster than the average student. These techniques are things that you can use on the SAT as well, right? Okay, using your calculator to benefit you. That's a whole other side note, but you should pretty much use your calculator for the whole SAT. All right, 43, what's up? Yeah, I mean, you could literally, for every math question on the SAT, you could probably answer it with a calculator. Every single, oh no. But for every, like those equations you solve on the SAT, you could solve every single one by graphing them and finding the roots, or just graphing and finding the intersection. And it takes like 20 seconds. So you could literally, I'm not kidding, when I was in high school, I probably answered every question with a calculator. I mean, things that you didn't have to use it for obviously didn't matter. But if there was like a quadratic, that might involve difficult factoring techniques. Graph the parabola, look for the x-intercepts, and those are your answers. Like, there's no reason to do a lot of stuff by hand.
Well,
So
that's
just
totally different than not like that bad, but it's still like. What? Like, no, that's each of it is different from like.
Oh yeah, it's definitely different.
Complicated.
There are problems that you can't use the calculator for.
What?
But if you
It's not
relax,
the same.
relax, it's okay. If you guys want to benefit from it though, there are certain problems that I definitely recommend go right to your calculator on. But obviously there's ones that, like when it talks about types of numbers, like whole numbers or integers, calculator's not going to help you on that kind of a question, right? All right, last. Let's draw in for F13 there. Let's cross this off. Put 43 newtons here. Put 43 newtons here. Let's do the last one in green. Let's do the last one in green, guys. Relax.
I mean, it changes the amount of they were all the same.
So for the last part, we've done already 1, 2. We've done 1, 3. Please stop, guys. It's 2 of you. We've done 1, 2. We've done 1, 3. Let's look at now 2, 3. Right? We haven't done F2, 3. Or F3, 2, really. It's the same thing again. So I'm going to do this again. I'm going to cross off my subscript. I'm going to write 2, 3 now. All right, that's a 3. 2, 3 there. Then, I know that this charge is now no longer 6. It's whatever charge 2 is, which was 1.5. The other one over here is still this, because this is charge 3. So this 2 remains the same over here. This becomes a 1.5 now for particle 2. So we've got Kc, particle 2, particle 3, over now, instead of 5 centimeters, how far are these two apart? 2 centimeters. Okay, we had 3 centimeters already. We used the full distance of 5 centimeters. Now we want this little distance over here of 2 centimeters. So particle 2 and 3 are separated by 2 centimeters. So I'll make this 0.02 squared. So obviously I'm showing you how you don't need to do this 4 times writing it out. Okay, write out the formula once, or write out the generics like I did on the right over here, and then after that you can just fill them in. So to recall again, this was 90, this was 43, and now we're figuring out this third one. Steph? 67.5. Agree, disagree? Can people check? Agree? Okay. So let's draw that on our diagram now. It's getting messy, I know, our diagram over here. 67.5 goes in here for F23. And it goes in here for F32. So our diagrams on the left are what are governing our answer at this point. Okay? Again, the diagram on the left is what governs our answer. So Mike, tell me, looking at the top one, particle 1, what's the overall force it's going to feel? (43 to the right, good. And what's to the left, though, Mike? So what's the overall force it's going to feel? Which way? Good. The first one feels 90 left and 43 right, so it's going to be an overall force of 47 left. Think about a balance. Which one is stronger? 90 is clearly bigger, so the net force has got to be to the left, and then just subtract the two. So, if we're drawing this down at the bottom here, oh, this is going to get messy. Hold on. Let me make sure it's placed. Okay, there we go. At the bottom, let's write down some statements here. So, the force felt on particle 1 overall is negative 47 newtons. That's a comma right here. Okay, next. The second particle. Looking at the second particle. It's getting 43, where are we? No, sorry, 90 to the right. Okay, the second particle is right here. It's feeling a pull of 90 to the right and 67.5 to the right. Since they're both to the right and they're both positive, we add them together, giving us a value of, good, 157.5, and that's to the right. Particle 3. Both forces are to the left on particle 3. So the net force has got to be negative. We know that already. We've got 43 to the left, which is right here. We've got 67.5 to the left, which is right here. We sum those values together and tack on a negative sign. What do we get? What do we get? What do we get? What do we get? Come on. 110.5. Simple math there. Negative, because it's to the left. All right? Now, do me a favor, add all three of those numbers together, see what you get. Add those three numbers together and see what you get. So I'm looking at my diagram, right? Remember these numbers we drew in? So this and this gives me this. It's negative because they're both left. This and this are both positive, adding up to this. And then the first one, one's positive, one's negative. Okay? Negative 90, positive. What do you get, guys? 0. Why? Why? Did it say anything about any motion?
No.
Are these objects moving?
No.
So the net force equals? Whenever there's no motion, when there's no acceleration, remember F equals ma, if there's no acceleration for each of these bodies, they are going to have a net force of 0. The system is in a state of equilibrium. Does that help some people that might have struggled on this for homework? Okay, the idea behind this, defining each of these, is a bit tedious, right? You're going to do a lot of math over and over again. But if you do more of these, it gets easier. Especially when you get to your problem set. How are we doing on time? Anybody know the bell for this period?
37.
37, 36? So we have a few minutes. Let's talk instead, okay? I'm not going to start another problem. We're going to